Welcome to Unit 4, the study of exponential and logarithmic functions. This is kind of a fun unit. I think there's a lot of fun things in here that allow you to do things that you couldn't do before. So I really like this unit. We are first going to talk about exponential functions. First of all, defining that, what that means, evaluating an exponential function, and then graphing the exponential function. We'll look at a later video to do the second two objectives that you see here. What's fun about this is that exponential functions show up a lot in the real world, quote unquote real world, right? Real applications in our physical world that we live in. One example of that is the situation that we're in with coronavirus currently. Remember, we used the phrase flatten the curve. And the question was, what does that mean when you hear, the question I'm asking is, what does that really mean when you hear that? Well, I grabbed this graph from this Statista website. I don't know if I'm saying that right, but the source is the Department of Health and Social Care. And these are the number of coronavirus deaths in the UK over these days from March 10th to April 7th. And what we see happening here and what we were concerned about is the growth of this. So if you look at this, we are growing pretty level here. And then all of a sudden it starts to take off, right? And if you think about projecting out what's going to happen here, this is going to grow very quickly. And that was the concern when we closed everything down. March 15th, it felt like everything shut down in the world because we were trying to flatten the curve, meaning we want to level it out. The goal was, instead of having this continue to grow forever and ever like this blue graph, was to say, okay, can we level this out some, flatten it? In essence, changing the path that we were following. So that's what that phrase really meant. Here, just a quick question for you. Looking at the graph above, the UK coronavirus deaths, approximate how many deaths occurred on March 30th. So we're looking here, right, going up here. It appears to be about, if you go over, about 2,000. Approximately 2,000 deaths on March 30th. Okay. Assuming the function modeling the number of coronavirus deaths in the US is given by C of t, where t represents the number of days after March 10th. Write this result in using function notation. Well, if we're talking about t representing the number of days after March 10th, March 30th is t equals 20, right? So we would say C of 20 is 2,000. The good news is that a lot of the work that we did with closing things down did indeed flatten the curve, and so that's the good news, right? But yeah, this is what we call exponential growth. Sometimes you'll hear people say the phrase exponential growth, and in your brain that probably means, ooh, that grows quickly, that grows a lot. But you may not know why. Well, it's because this blue function, if we were to continue and we didn't flatten the curve, then that blue function represents an exponential function as defined down here in the middle of the page. A function of the form f of x equals a to the x, where a is a positive number and x is not equal to 1, is called an exponential function with base a. We need that a to be positive And if it's 1, it's uninteresting, right? 1 to the x is just a constant function. It's always 1, no matter what x is. So that's why we exclude x equals 1. We need it to be positive because you can't have a negative inside with some exponents, right? The difference between what we see here and what we have seen in other functions is that our variable is in the exponent here. That's what makes it an exponential function. We have a constant base. I give you a couple of examples here. F of x equals 5 to the x and g of x equals 1/2 to the x. F of 2 is going to be 5 to the second, or 25. The variable is in the exponent. G of 2, 1/2 to the second, replacing the x with 2, is 1/4. Let's try f of negative 1/4. That is 5 to the negative 1/4 power. We need to think about what that means, and is that okay? I said that the a itself had to be positive. That's this. We're okay with that here. We have a is 5 in f, and a is 1/2 in g. Both totally fine. Is this x being negative a problem? The answer is no. We can have negative exponents. It just means it drops it into the denominator, right? And then the 1/4 power is the 4th root of 5. So that is f of negative 1/4. A little bit of review of rules of exponents. The negative exponent, we'll put it into the denominator under 1, and then the fractional exponent, that denominator is the index on the root. So that's why it's a 4th root. I wanted to look at graphs of exponential functions. Let's start with f of x equals 2 to the x. When we don't know what something looks like, we generally will do like a table of values, right? It's not ideal, but it will give us a picture. We just said that it was okay to have negative exponents on there, so we can have negative x values. So let's figure out what happens. 2 to the negative 2 is going to be 1/4, because the negative 2 drops it into the denominator. You have 1 over 2 squared, or 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. And 2 squared is 4. Let's plot those points. When x is negative 2, y is 1/4. So it's super close to the axis down here. When x is negative 1, y is 1/2. When x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. And you can imagine if you kept going, 2 to the third is 8. So that goes up pretty quickly. Just moving over one space, it now goes all the way up to here. So that's where we're talking about exponential growth, growing super quickly. The next one, if you did 4, would be 8. What happens if we keep going the other way? Negative values. 2 to negative 1,000 is 1 over 2 to the 1,000, which is a really big number in the denominator, but it is always positive, right? No matter what exponent I put on 2, it will never be a negative number, meaning I cannot go below the x-axis. It will also never equal 0. 2 to any power is never actually going to equal 0. So this function, these numbers do get tiny because the denominator gets bigger. It gets closer and closer to the x-axis, but never actually touches it, which makes the x-axis a horizontal asymptote at y equals 0. That x-axis gets closer and closer and closer to it as x goes to negative infinity, but it never actually approaches, or never actually touches it. It approaches it, doesn't touch it. That picture that we just drew there looks pretty similar to what we're seeing in this graph, huh? If we didn't flatten the curve. Okay. This one's a little different because now we're looking at a situation where that base is between 0 and 1. So we're looking at this fraction. Let's do the same idea here. Generally, I don't like tables of values to figure out what a function looks like. But when we don't know, it gives us a good idea, and then we can think about what happens if we did other values. Okay, 1/3 to the -2 is 3 squared. You reciprocate it with that negative, so it's 9. 1/3 to the -1 is 3 to the first. 1/3 to the 0 is 1. 1/3 to the first is 1/3. 1/3 squared is 1/9. Okay, let's plot those. -2, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up here. -1, 3 is here. 0, 1. 1, 1/3 will be about here. And then 2, 1/9 is going to be here. We have a similar picture to what we had before, except it goes the other way. The same concept applies here, that this is going to approach the x-axis but not actually reach it. That looks pretty yucky there. It's a nice smooth curve down here. Nice and smooth. So that's what these look like. With the base between 0 and 1, it decreases. With the base greater than 1, like this, it increases as you move from left to right. They're kind of a mirror image of one another. Let's talk about some properties of f of x, this exponential function a to the x. We talked about how it doesn't matter what x is. You can put any exponent on that you want. You can put fractions, you can put negative numbers, doesn't matter. The range of that, however, is 0 to infinity. So we're talking about y being greater than 0. Because no matter what I plug in for x, a to any power cannot be negative, where the a is positive, which is a requirement. We say the function is 1 to 1. Do you remember what that means? When, back in Unit 2, we studied inverse functions, it told us that it has an inverse function. That concept is going to be important. Exponential functions have inverse functions. Might be a good idea to go back and review some of that information about inverse functions at the end of Unit 2. Look through those notes that you have there. The x-axis is a horizontal asymptote. We already talked about that. And the y-intercept of this particular function, with no shifts, no stretches, no transformations on the function, will always be 0, 1, because when you plug in 0 for x, anything to the 0 power is 1. A function is increasing for a greater than 1, and it's decreasing for a between 0 and 1. Those are some properties of exponential functions without any transformations on it. However, we can transform this around the plane to give us other pictures, and a lot of real life applications do have some sort of translation. If you look up here, this function, maybe it does. This definitely has some, I'd have to look. If we're calling March 10th 0, I have to look at the actual numbers to see if on March 10th, is that the ordered pair 0, 0, or is it 0, 1, right? If it's not, then you've got something going on. If it's not 0, 1, then you have something going on that is causing a stretch or shift there. So I'd have to look at the raw data. It's too hard to tell from just that graph. Okay, let's talk about the transformations that we see here. The H would shift it right or left, depending upon if it's added or subtracted. Right, because that's added to the X. The direct addition or subtraction to the X is a right or left shift. Then order of operations, I'm looking at that B. So that's what the H would do. The B is a shrink or stretch. And it could be a reflection if it's negative. And then the K is a shift up or down. That's that vertical shift. Okay, so we can transform this around the plane. Let's take a look. It says describe the relationship between f of x equals 2 to the x, which we graphed up above, and g of x equals -1/2 times 2 to the x minus 4 plus 3, and then state the domain and range of that function, g of x. An important concept here is that once you do translations, it can change domain and range. Let's take a look. Let's talk about the translations first. I always like to follow order of operations. So think of plugging in a number for x. The first thing you would do is subtract 4. That shifts it right 4 spaces. Remember that horizontal shift is kind of the opposite of what you would expect. You think -4 would go to the left, but it's the opposite. Then the 2 to the x is what you, or 2 to the x minus 4, whatever that number is what you would do next. That is the function itself. That shows that general shape. Then we shrink by 1/2. That's vertically. Right? That's changing the y coordinates by 1/2, dividing them by 2, multiplying by 1/2. Reflect over the x-axis from the negative, and then shift up 3. That's that last one here. The question now becomes, how do these things impact the domain and range? The domain itself is not changed at all. There's still no restriction on what you can plug in for x. Subtracting 4 from it doesn't change what that exponent can be. It changes what it is, but not what it can be. So no issues with the x there. The range is going to change with this, though. I want you to think about, just generally, we're going to do a rough sketch here. This is 2 to the x, something like this, right? We know that this y equals 2 to the x has a range of y greater than 0. It can never be negative. Shifting it right 4 spaces doesn't change that. The horizontal asymptote still stays the same place. Shrinking it doesn't change that. It just brings all of the values closer to the x-axis. Now, once you reflect it, your reflection now flips it down this way, right? Rough sketch, total rough sketch here. And so now with the reflection, my range becomes that I only have negative numbers. Y is less than 0. Now when I shift it up 3 spaces, if I go up 3 spaces, the asymptote, shifts with it, right? Oh, geez. So I have something like that, and that makes it so that y is less than 3. I do have increased y values now. So now my range is going to be negative infinity to 3, not including the 3 because the horizontal asymptote is now at y equals 3 with that vertical shift.